Welcome to 1010 of Hayton and Buck, 8th edition, VSWR, Voltage Standing Wave Ratio. And it's nice to know why we're studying this right now, because there's a lot of algebra, some of which I'm going to do in the video, and some is too long and complex, and you'll have to read it in the textbook. So let's see what happens here. I'll say it in words before I write any equations. Generator generates a voltage. It's a source, and the combination of the generator and its impedance are matched to the transmission line, which we should indicate has impedance Z0, and that feeds the load. Now, why do we want to learn this? Because we know that when Z0 and ZL are not the same, there's going to be a reflection at the load, and that's going to send a wave back to the generator. So we really don't want this, but we need to know how it comes about. So the first thing we do is we launch our wave from the generator, and I'll call that VI as before, and it has an amplitude V0, e to the minus j beta z. Seen that before? V0 could be a complex number because we're in the phasor notation. It doesn't strictly have to be real. This allows us to switch between sines and cosines or their combinations. Now, it's reflected, so we use VR. So we've learned from the previous section that the magnitude of the V0 now is weighted by the reflection coefficient times, so there's our new amplitude, could be complex, and we know that it's going in the opposite direction, so no minus sign, j beta z. So now we can write the total, which is the sum of these. And what is that? Well, it's a straight addition. I think you can see that I can factor out a V0 when I add the two, and the text calls this VST of Z. And I'm going to do the algebra right now rather than later, even though this is not quite the same as the equation in the book where they don't do the algebra. So V0 factors out. Plus gamma times that's the total transmission line voltage, and that's equation 8 Buck, edition 8, number 79. Just to remind you, the reflection coefficient, gamma, is equal to the load impedance minus characteristic line impedance, the difference, divided by the sum. And that's going to be equal to, it could be complex, and that's equation 80 in the book. It should be 8, and that's 80. Now, we see now why we want to study VSWR, because if we know gamma and we know the characteristic impedance of the line, then we can figure out what the load is. So that means you don't have to do measurements of the transmission line voltage at the end. You may not be able to if it's 100,000 volts at the load. You don't want to be there. So this is a way of doing measurements. Now, turns out we're going to be able to measure gamma and phi. And when we do that through the measurements, and we'll see that in a minute, then we can construct and find ZL. Now, what does this depend on? Well, it depends on this equation here and its characteristics. And so that's what we're going to look at. And some very, very nice things happen. So let's look at that. And if we look at this and rewrite it, so it's really interesting to rewrite that equation and then take the real part after multiplying by e to the j omega t, so we get the instantaneous value of the wave. Then what we're going to see, it's decomposed into two pieces. So the total real wave is, I'm going to write it script script st, well, not st, just script, no subscripts. It's not complex. It's the real part of the wave. So it's going to be in z and t. It's the real voltage wave. And I'm not going to write all the algebra. I want to, because that's in equation 84 in the text. So I'll write the equation reference for you, but the intuition is what's important here. So we get 1 minus gamma times a traveling wave, plus gamma times a standing wave. So that's what happens. So let's look at some examples. What happens if you have a line that's open circuit? So ZL is infinity. So what happens there is gamma is equal to infinity over infinity, which is 1. So what happens to the traveling wave here? The magnitude of gamma is going to be 1. And this means that this term, traveling wave, vanishes. So you just get a standing wave. A standing wave, and there's a video that I'm posting to show physically what a standing wave is. It's just a wave, like a sine wave like this, and it's fixed, and it just oscillates up and down. And where the zeros of the sine wave are, those are the nodes, and they stay fixed. And so you just have energy not moving. It's just bouncing up and down in a sinusoidal envelope. And I will show you the picture now. So what a standing wave is going to look like, let's draw it here. So we got, at one time it can look like this. And at another time, it'll be upside down, like that. And I'm not doing the algebra here. So as time goes, we swap between the positive and negative like this. And you can see that in the video, and I have that referred to in edX. It's an old AT&T video, and it is really fantastic. So you can actually see what's going on. One of the problems with this stuff is that you can't see what's going on. So you have to say that waves all behave the same. So let's look at a wave we can see, mechanical wave, and that's what's in the AT&T video, and it's referred to in the course notes. Okay, so now we can see what's going on. So if gamma is perfect, you have a perfect reflection with the magnitude of gamma equal to 1, you only get a standing wave. If gamma is 0, then you have only a traveling wave. Well, if gamma is 0, there's no reflection, so all the energy goes into the load, which is what we want, but we often don't have, so we'll have to fix it. But in order to fix things, we need to somehow measure what the magnitude and the phase of gamma are. And how do we do that? Well, we have to look at this equation. And what I'm going to do is I'm going to erase some of the other equations, and we're going to analyze this equation. So let's do that. I will just erase this quickly, not using the water. So it will just give us some more room to play with here. And what's interesting is the intuition around this VSWR stuff. So the key equation is to my right, and it's equation 79, absolute key. And we're going to look at simple properties of that equation, and we're going to get gamma out of it. And I'll do some of the algebra to show you how you do that. I'll leave the picture of the transmission line on, and I'll leave this because this is the intuition. Now, I want to know when the magnitude, the amplitude of VST is minimum. All right, so the amplitude of VST is minimum amplitude VST of Z. It's minimum when the phase difference between the wave traveling to the right and the wave traveling to the left are out by 180 degrees, pi, and multiples of pi. So when that happens, let's see where that happens. So what we want to do is write the phase difference between forward and backward traveling waves. So what's the phase difference? It's going to be, well, the phase of the launched wave is beta z. And we're going to subtract the phase of the traveling wave. But it's kind of messy here, so gamma could have a phase factor in it. So we have to modify this to stick in the representation of gamma's complex number. So modulus of gamma times e to the j phi. So the phase of this second term is the phase of the reflection coefficient added to the phase of the wave traveling back. So subtracting it, it's minus, there's the phase of the wave traveling to the left, plus, from here, the phase of the reflection coefficient. So this is very straightforward, and that's equal to odd multiples of pi, 2m plus 1 pi. I'm going to actually do the algebra slowly so you can see it. And then if we want to do the maximum, then the phase difference, they can interfere constructively. And this will be just multiples of pi. So they're all in phase. There's no subtraction because when you're out by pi, troughs and peaks are canceling each other out. But they're not going to perfectly cancel because of this, depending on what that is. So let's see what happens is simple algebra. And we get minus beta z, so that's minus 2 beta z. And let's take the phi to the other side. So then minus 2 beta z is equal to phi plus. And I'm purposely going slow here so there's no magic things because the book actually just writes it out and doesn't really, it says phase difference, but it's nice to see it done and that it does actually work. 2m plus 1 pi. And m in the book, m is equal to 0, 1, and so on. So that's going to always be an odd number of pi's. And now we can solve for this, so that will give us the location of where the phase difference between the forward and reflected wave will partially cancel out. So let's have a look here, just finishing the job. We'll say that z is equal to minus 1 over 2 beta times phi plus 2m plus 1 pi. And that's equation HB8, 8 number 86. So this particular Z is where the minimum amplitude occurs, min. So now what is that minimum amplitude? Well, the minimum amplitude is going to be where this wave, these e to the j beta z's plus or minus have amplitude of 1. This has amplitude of gamma. This guy is going to cancel this guy, so you have a minus sign here. So that's going to be the minimum amplitude. Now, I don't want to be too boring here, but it's really nice the way I've set it up is we can easily do the maximum. So let's do the maximum. And all I have to do is erase a little bit. So if we have max, max amplitude VST, same argument as before, but now the phase difference is just multiples of pi. That means the peaks and peaks are going to add and still have a minus here. So we just replace 2m plus 1 by 2m. And write max here. Z max. Great. Now, what's left is to write down what the min and max are and then actually see where the measurements come in. So one thing I want to make right away, from HB86 we can, or this is 89, sorry. From HB89 we can measure, we know what the voltage is, so we have some measuring device that we move from the load and measure its distance. That's Z max. M will be 0, so we can get phi. That means we got the magnitude of the value of the phase. We just need the magnitude. Well, how do we get the magnitude? That's where we define the VSWR. That gives us the magnitude. Remember that this whole exercise is depending on this so that we know what magnitude and phase of gamma are, and then from the reflection formula we can figure out what the load is. So now it's a simple algebra, but we have to define what the VSWR is. So let's keep all this here. We know what these locations are, so that's a given. We're working on the amplitude. Locations of the max will give us phase. Now we need amplitude, so that's the next step. So what is the minimum value of the amplitude? Well, of the total voltage. And what is the maximum value? I think it's fairly clear how that's going to go. And then there's a graphical way to do this by using representation of complex numbers. And that's going to be a class exercise. All right, so I will just give sort of the intuitive description like the book does. And unfortunately, there's no diagram, but that's going to be a class exercise. Right, so now, what is VST at the location Z max? We want to know what the maximum value of this is. Well, let's look at here. So if they add in phase, so this has a max value, if you think of its sine and cosine of 1, as does that. So it's going to be, it's the actual amplitude, so it's going to be magnitude of V naught, if V naught is complex, times 1 plus magnitude of gamma. And the minimum, I think you can see, this is max amplitude, not the min amplitude of VST at Z min is going to be V0 into 1 minus gamma. Well, we're almost done here. All the hard work is done. We know what that is from the locations. We did that before. We now have this, so we're going to define VSWR, and you actually can have a VSWR meter. And so VSWR is defined to be, use the letter S often, is equal to max amplitude of V, and that's VST, min amplitude, and what is that? That's equal to, when you take the ratio, the V magnitudes of V naughts will cancel out, and we'll get 1 plus magnitude of gamma divided by 1 minus magnitude of gamma. So we've got to measure this. So we have a VSWR meter, and we know the value, and you could solve for this magnitude of gamma. And it's a simple algebra to show that. I mean, this, I don't have to do it. S times 1 minus magnitude of gamma equals 1 plus gamma, and you rearrange it, and we get this. S minus 1 over S plus 1. You can see that from here, you're going to get minus gamma times S and bring it over to the other side to add to the magnitude of gamma. So factoring it out, you get S plus 1. So there it is. Now, we've got gamma, we got phi, we got magnitude of gamma, we got phi, so that means we have gamma. That means we can get the load. And how do you measure it? Well, what you do is you actually, in some lines, you have a slot in the line, a little measurement meter, and you find the maximum wherever it is. That gives you Z max. You know at Z max, you know where it is because you have the little meter, and you can measure phi from the Z max equation, and you can see the little needle of the SWR meter, and it goes clunk, max. So now you know what S is, and from this formula you get this, and we're done. And so now we have a way to do the measurement of gamma. And the next thing we want to do is we want to take this equation and the current equation, write them, and look at the wave impedance again, but this time we're going to do some graphical wizardry to look at what's called the Smith chart.